Okay, recording now. So I forgot to change the document title. This is not describing center, this is describing spread. So when I give you a quantitative display and tell you to discuss center shape spread unusual, previous half hour was talking about center, now we're going to talk about spread. Before we can talk about interpreting spread, you are going to have to really thoroughly understand where spread comes from. This is our spread number. You get it on the exact same screen as you get your average number. So when you do one variable stats, and we got X bar and median from the previous screen, we're also now getting the spread. So this thing here is going to be our measure of spread. This is not so much a straightforward calculation. Okay, so we're going to walk through how that number gets calculated, but the good news is it's going to be the same thing as before. You have to know the formula. You have to know how to substitute into the formula, but you're going to have your calculator do all of the grinding through the grunt work of getting the spread number. So in this table, here are the same set of data. These are the quiz scores. So I'm going to write quiz scores. Okay. And the first thing we did was we added them up. And I think we got 15, 25, 35. We got 35. And then when I divided it by n, we got 35 divided by 7 is 5, and we called that X bar. Okay, that was the sample mean. So we already did that. What is the deviation? Deviation is defined as the distance each value is from the center. How much does each quiz score deviate from the center? Well, the person that got a 2 minus 5 is, hold on. Anybody notice a typo? No, so you're all dyslexic like me, huh? All right, two numbers got interchanged. There were not 7 quiz scores, there were only 5. So that number down there is supposed to be a 5, which means at least I did 35 divided by 7 correctly, but it should be 35 divided by 5, which is 7. So the average on that quiz was 7. So you're all processing this as I go, huh? Yeah. Checking for silly mistakes, making sure I don't screw stuff up. All right, anyway, as I was saying, deviation is defined as the difference between the piece of information that you have and the center. So the formula is X, which is the data, compared to X bar, which is the average. So 2 minus 7 is -5. That person already knows that he or she scored 5 points below the average. 4 minus 7 is -3. The second person scored 3 points below average. 6 minus 7 is -1. 8 minus 7 is 1. And 15 minus 7 is 8. So the question is, can I use that column to figure out how much the class on average deviates from the center? Can I take those numbers and figure out what the typical or average deviation is? Remember, we're trying to find spread. So wherever the center is, I want to know how much variability there is around that center. Are the quiz scores close to the average, or are they all over the place? Okay. Well, what do you think I should do with that column? What did I do with the previous column? Previous column, I added them up and divided by 5. This column, I'm going to add them up. I'm going to get -8, -9, -0. Oh, that's not a good sign. That's always going to happen. Okay. If you take each piece of information and compare it to the center, you're going to get deviations, but the sum of the deviations is always going to be 0. So the first useless formula is this. The sum of the deviations is always 0. And that makes sense because the mean sits in the center of all your numbers. Some are going to be above, some are going to be below. The mean is going to sit in the center, which means when you tally up all those differences, they're going to cancel each other out and you're going to get 0. So if you read the title of the next column, guess what we're going to do with those deviations so that they don't cancel out? we're going to square those numbers. And if you are processing this, and if you are thinking about the process that's going on, you might have a question right now, but maybe you don't. Those will not sum to be 0. Let's see what those sum to. 25, 9 plus 1 is 10, so that's a total of 35. 36, 36 plus 64 is 100. Okay. Is there another mathematical way of getting those deviations to be all positive besides squaring everything?
Absolute value.
Absolute value, right. So some people at this point here say, well, why would you square those numbers? Why don't you just take the absolute values and sum them up? And there is a very small, tiny, obscure corner of statistics where they use the absolute value for deviations. Almost everyone does not use that process because, and this gets a little bit technical, the absolute value does not have a unique minimum. If you take two absolute values, I don't know if you did this in your advanced algebra pre-calc class, if you take two absolute values and add them together and then plot that, you might not get a V, which is what absolute value looks like. You might get like an edge, a flat bottom, and then an increase. So because adding absolute values do not produce a single minimum value, mathematicians and statisticians said, no, we're not going to use that. We'll just use square deviations. The idea behind square deviations is that this is a parabola, and parabolas always have a single unique minimum. So that's why we do square deviations. So those of you that are statistically curious, that's why we do squaring. That won't ever appear on a test or quiz. So, all right, we have a total square deviation of 100. That's great and fine, but if I had a much bigger data set, that 100 number would be much bigger. So how do I cancel out the size of the data set? Well, normally you would do this. Wait, hold on. I think we need to, checking my notes here. How much space do I have? Plenty of space, good. Okay. So from this point here, I'm gonna put an arrow over here. We gotta go through a slight detour, okay? And you'll see why in a second. So our measure of variability is the sum of the x minus x bar squareds, okay? That's fine, but the bigger the data set is, the bigger that number is. And so I wouldn't be able to compare, different size groups. In other words, if Prospect has 2,000 kids, and if, what's a small high school? How big is Vider? They're not 2,000, are they?
Like 900.
900? Okay,
Yeah.
so let's say we wanted to compare something between Prospect and Vider. Our variability would be much larger because we have 2,000 pieces of information, whereas their variability number would be much smaller because they only had 900. That doesn't mean that they're less variable. It just means that in order to calculate the variability, they had fewer numbers to sum. So the way that we cancel out the effect of the population or the sample size is we divide by n. So we call this average deviation. So we take that. And see, if I just gave you these formulas, they'd look awfully intimidating. And you'd say, my God, there's Greek letters there, and there's squaring, and there's ends, and I don't understand what's going on. So if I build the formulas, the hope is that you feel a little bit more comfortable. So that would be the average deviation. But then in the big bright red, we're going to put a frowny face. And that's not statistically important, but it is kind of important. This, unfortunately, is biased with respect to sigma squared. Sigma squared is the population variability number. I'm going to pause. I'm going to let you write that down because this is where things get a little bit strange and kind of abstract. And I have to review a couple things that we haven't done in a while. Everything I'm writing in blue now and everything I'm talking about is certainly testable. Okay, these are ideas that you got to know. Okay, so it looks like everybody's done writing. So here's the story. When I discussed the word bias way back a long time ago, I said it doesn't mean prejudice, it means that you're missing the mark. And one of the examples I talked about was maximum. If I have a list of numbers and if I take samples and in each sample I find the maximum, if I compare the maximum from all those samples, it is not going to be the same as the population maximum. Okay, it's really hard to get a population maximum from samples, which is why in Stats 101 we don't discuss maximums a whole lot. We do need a measure of variability, but unfortunately, the one that makes sense, comparing every piece of data to the average, squaring it so that it's positive, and dividing by n to get a typical amount of squared variability doesn't work because this quantity underestimates the population number. Okay, it doesn't work. It's not good enough. Here's the good news. You don't have to know why. You do have to know that you don't have to know that it's too small. All you're going to know is how we correct it. So we correct it by taking and if I reduce the denominator by 1, it seems like kind of an arbitrary random number. Okay, if I reduce the denominator by 1, that number is unbiased. That number works. Okay, so I'm not going to go through why n-1 works, but n doesn't. It's a bit of an icky process to explain why. But I heard one person tell a story. If you think about fence posts, if you have 2 sections of fence, you're going to need 3 fence posts, beginning, middle, and end. It's kind of like that with data. If I have 3 fence posts and if I subtract 1, that means I can support 2 sections of fence. So with data, if I have n pieces of data, n-1 is all I need to get the true estimate of variability. Okay, so this is called without proof. I'm telling you that n-1 is what we need and not just n. And we have one more tiny little issue. Okay, quiz scores are measured in points. So if I found the average quiz score is 7, the units I'm going to attach onto that are points. The average quiz score was 7 points. If I calculate variability by calculating the deviation and then squaring it, now my units are messed up because now I'm talking about variability in squared points. So to fix it, we undo what we did earlier, take the square root of that thing, and because of order of operations, it's not going to be the same thing. I'm going to have to add all those things up. Sorry, I'm going to have to square all those things, add them all up, divide by n-1, and then square root. Okay, so it's not quite a thing there. And then now finally we have a famous useful thing. S is called the sample standard deviation. And it is our unbiased measure of variability. That's so important. I'm going to put a purple highlighted box around that section there. There, that's a formula for the sample standard deviation. You almost never, and I can't really say never, but almost never are you going to have to calculate the sample standard deviation by hand. It's just too much of a time waste, okay? You have to know the properties. You have to know that you're taking deviations, squaring them, summing those numbers together, dividing by n-1 so that it's unbiased, and then square rooting to fix the units. But that's how we're measuring spread. If we have a standard deviation of 15 for prospect and a standard deviation of 18 for Viator, they're more variable than us because their standard deviation is larger than ours. Okay, by dividing by the number of students minus 1, the size of the population or the size of the sample doesn't matter. All right, I got to do one more small thing. How much time we got left? 15 minutes. So I'm gonna do one more small thing and then we can take our foot off the pedal a little bit. Everybody caught up with their writing? Okay.
Yeah, wait, really quick. So for the example above, if we were trying to find the like S, would we take 100 over 4 and then find the square root of that?
Yep, I was just about to do that. I was going to point to the calculator one first, and then I'm going to show you how to calculate it for this thing here. So,
Got it.
all right, so yeah, let's go through that now. Okay, so according to the calculator, our standard deviation, the symbol on the calculator is S. That's supposed to be a subscript, but S sub X is 5. Okay, the calculator does something that's a little bit annoying. It's going to give you what it thinks is the population number, that sigma. Don't ever read the sigma off your calculator. Okay, there are many, many, many stats people that wish the TI wouldn't put this on here, but we are not, that is not the population number. Okay, they can, what they're trying to, they're dividing by n, and they're saying, well, if we divide by n, then we can give them sigma, but it's not really the population number. Okay, so the warning I have is that if you're asked to find the sample standard deviation, if you're ever asked to find a standard deviation, use the S number, not the sigma number. Okay, so if S is supposed to be 5, let's see if that jives with our calculations here. So now that we've gone through this detour, let's go back and finish this. So 100 was the sum. I'm going to start with the formula. S equals the square root of x minus x. Oops, I forgot my summation. Sum x minus x bar squared over n minus 1. So it should be the square root of the sum of x minus x bar squared was 100. I had 5 pieces of data, so I'm going to take 100 divided by 5 minus 1, which gives us 100 divided by 4, which I think most of us know is 25, which simplifies to be what? 5. And look, it matches. Yay. Okay, that's why this data set is famous, because you can calculate the standard deviation by hand without a calculator. And we just verified by hand that the calculator is giving us the correct number for the sample standard deviation. And notice that the symbol that we give it is S, and the units are the same as whatever you measured it in. This would be 5 points. I'll include the smiley face inside the box. It's kind of, if you put a smiley face next to all your answers, maybe you feel good about your answer, even if it's not correct. And again, that's all we care about, is how you feel about math. I saw 2 people smirk, so maybe you are listening. All right, so Jenna, did that answer your question?
Yep.
Okay. Anybody else question? Going once, going twice. No. Okay, checking my notes. I think we tackled everything. I'm gonna get this silly. That thing out of the way. Okay, all right, I'm glancing at time and trying to figure out, yeah, we can do both of these things because these are quick. All right, by far, much less important. And I will put it in green. No, actually, I'm gonna put it, what color would you choose for something that's not important? Probably orange. Not even writing that important. There are some people that do x minus median squared. Okay, that would be 16, 4, 0, 4, and 81. Okay, that's 105. One of the reasons why we use the square deviation, that thing there, is no matter what process you use, this number here will always be a minimum. Okay, so if you do another deviation process using the median or using, there's something called the mid-range, no matter what other process you pick, the squared deviation will always give you the smallest possible squared amount of variability. So that's something that we kind of want, I guess. It's kind of hard to explain, but that's just demonstrating that you could pick a different method, but it's going to produce more variability. And then lastly, everybody okay with the screen? Can I leave this? Okay, lastly, let's go back. I forgot to highlight something in the other note page. So whenever we look at real data, it's kind of interesting to figure out where we're at. I had the software spit out the prospect value for how much we spend per pupil, 12,405. So if I put that in, guess what color I'm going to put it in? Lovely Columbia blue. I made all of our graphs blue on blue so that it matches our school colors. So, I mean, I really did. I made that plot and I picked those colors specifically. Where is $12,405? Here is 13,000, which means 12,500 would be here, which means 12,400. PHS, expenditures per student, is right about there. So if I zoom back, are we above average? Yes. Are we far above average? Yes. Okay, so are we in the top 10? I don't know. Okay, there's a whole lot of schools. I mean, there's a school that's pushing $15,500. So it's kind of hard to compare apples and oranges. And I did mention Viator a few minutes ago. You obviously don't charge tuition. Sorry, we obviously don't charge you tuition to come to the school. Viator does charge tuition. So if we needed to maybe compare a way of, how much we're spending per school, you could possibly say, well, Viator's tuition is that and compare it to our expenditures per student. So we're roughly $12,405 expenditures per student. Now, I'll warn you that that's not a great comparison for a couple of reasons. First of all, when somebody pays tuition for a private school, that goes to cover everything, not only instruction, but also like heating and maintenance of the facilities and other non-educational things. Whereas I believe this $12,405 is only for instructional expenditures. So paying for teachers, paying for supplies. I don't think that includes buildings and grounds and other things like that. So you can't really compare our 12,405 with whatever Viator's tuition is, but we can within the public schools can compare a prospect to other schools. And again, this is everybody in the state. We are not, not the top bunch. There's a bunching at the top that's way up there. We're not there, but we're pretty close. Why are there so many schools down at the left end near the mound part of the distribution? Well, because downstate things are a little bit less expensive than they are up here. You're living in probably one of the more expensive areas to live. So everything needs to cost and spend more. Cook County taxes, City of Chicago taxes, and I know we're not in the city, but Cook County taxes, City of Chicago taxes, everything in this area is more expensive. So it would make sense that schooling you is also going to be a little bit more expensive. So the final thought on this is at some point, there's going to be a borderline between when we say, all right, well, that's high, but not unusual, and this is extreme or an outlier. One of the things we start, now that we can measure variability, we can start to put lines on things and say anything that's above there is an outlier, while everything left of that is typical or not extreme. So we're gonna have to find a borderline that says you are significantly more expensive or you are spending a significant more on your students than the rest of the population. So that's one thing statistics does. It says, where's the borderline between something that's extreme, that's an outlier, that's significant, and where do we just have values on the high side? So that's kind of what we're aiming towards. All right, I think I am done babbling. Any questions about anything we've gone over? Going once, going twice. Okay, you're awfully quiet today. It is Wednesday, which normally isn't a low energy day, but maybe you're just haven't recovered from Tuesday. All right, let me take one last glance at my notes and all right, I did leave out one diagram, but I don't think that diagram is important. Okay, so let's do this then. We have 7 minutes left. I'm going to stop talking. Why don't you, I'm not going to put you in breakout rooms because by the time you get there and get acclimated, it's going to be time to go. Jot down what you can for the examples on the back of the first worksheet. I'm going to turn off the recording because they don't need to hear this. But just jot down some answers to A, B, and C. And then at some point we'll discuss those. But congratulations, you made it through 2 sections today.